Understand the initial state of the system. The chemical reaction is CO plus 2H2 is in equilibrium with CH3OH. The gas mixture is at dynamic equilibrium in a 2.0 liters vessel at a constant temperature of 483 Kelvin and exerts an initial total pressure of 1.2 atmospheres. Calculate the instantaneous effect of reducing the volume. Boyle's law: the volume of the rigid reaction vessel is reduced from 2.0 liters to 1.0 liters. According to Boyle's law, PV equals constant at constant temperature in moles. Having the volume of a gas mixture immediately doubles the partial pressures of all individual gases. If no chemical shift were to occur, the total pressure of the system would instantly double from 1.2 atmospheres to exactly 1.2 atmospheres times 2 is equal to 2.4 atmospheres. Quad apply Le Chatelier's principle to the pressure increase. Having the volume increases the overall concentration and total pressure of the system, creating a pressure stress. According to Le Chatelier's principle, a system at equilibrium subjected to an increase in pressure will shift its equilibrium position in the direction that minimizes this pressure by producing fewer moles of gas. Compare the moles of gaseous reactants and products. Reactants: 1 mole of CO plus 2 moles of H2 is equal to 3 moles of gas products. 1 mole of CH3OH, since the forward reaction converts 3 moles of gas into 1 mole of gas. A shift to the right decreases the total number of gas molecules in the vessel. Therefore, the equilibrium will shift to the right, the forward direction. Determine the final equilibrium pressure. As the system shifts forward to produce more CH3OH, the total number of gaseous particles in the vessel decreases, which lowers the total pressure below the instantaneous peak of 2.4 atmospheres. However, Le Chatelier's shift can only partially relieve the applied pressure stress. It cannot completely counteract the effect of having the volume. Thus, the final equilibrium pressure must remain higher than the original equilibrium pressure of 1.2 atmospheres. Combining these bounds, the final total pressure of the system will be greater than 1.2 atmospheres, but less than 2.4 atmospheres, which is option B. The correct answer is option B, greater than 1.2 atmospheres, but less than 2.4 atmospheres.